Hello everyone, we are going to learn about orthogonal system in complex analysis. This is lecture number 7. Orthogonal system. Two families of curves u of xy is equal to c1, v of xy is equal to c2 are said to form an orthogonal system if they intersect at right angles at each of their points of intersection. Theorem. If fz is equal to u plus iv is an analytic function in a domain D, prove that the curves u is equal to constant is equal to c1, v is equal to constant is equal to c2 form two orthogonal families. Verify this in case of function fz is equal to sin z. Proof. First part. Let fz is equal to u plus iv be an analytic function of z. Show that Cauchy-Riemann equations ux is equal to vy, uy is equal to minus of vx are satisfied. Suppose that m1 is equal to slope of the tangent to the curve u is equal to c1, m2 is equal to slope of the tangent to the curve u is equal to c2. If we show that m1 into m2 is equal to minus 1, then the result will be proved. Taking differential of u is equal to c1, v is equal to c2, we have du is equal to 0, dv is equal to 0 because u and v are constants, or del u by del x into dx plus del u by dy del u by del y into dy is equal to 0, and del v by del x dx plus del v by del y dy is equal to 0. Therefore, m1 is equal to dy by dx. From this expression, m1 is equal to dy by dx is equal to minus of del u by del x by del u by del y is equal to minus of ux by uy. And from second expression, this second equation, m2 is equal to dy by dx is equal to minus of del v by del x by del v by del y is equal to minus of vx by vy. Hence, m1 into m2 is equal to ux by uy into vx by vy, because m1 is equal to minus of ux by uy and m2 is equal to minus vx by vy. So their product is this is equal to minus vy by uy into uy by vy, because ux is equal to vy and vx is equal to minus of uy. So ultimately we have m1 into m2, this is equal to minus of 1. Second part. Let fz is equal to sin z. So u plus iv is equal to fz is equal to sin z. This is equal to sin of x plus iy because z is equal to x plus iy. is equal to sine of x cos iy plus cos of x sine iy. Sorry, this is cos of x into sine of iy. Cos of x sine iy. This is equal to sin x cos hyperbolic y plus I times cos x sin hyperbolic y, as cos of iy is equal to cos hyperbolic y and sin of iy is equal to I times sin hyperbolic y. Therefore, separating real and imaginary parts, we have u is equal to sin x cos hyperbolic y is equal to c1 say, and v is equal to cos of x sin hyperbolic y. This is equal to c2 say. Differentiating both with respect to x, we have cos of x into cos hyperbolic y plus sin x into sin hyperbolic y dy by dx is equal to 0 for this, and minus of sin x into sin hyperbolic y plus cos x into cos hyperbolic y dy by dx for second curve, this is equal to 0. Therefore, from first equation, m1 is equal to dy by dx 1 is equal to minus of cos x cos hyperbolic y by sin x sin hyperbolic y, and from second equation, m2 is equal to dy by dx 2 is equal to sin x sin hyperbolic y by cos x cos hyperbolic y. Multiplying these two, we have m1 into m2 is equal to minus of cos x into cos hyperbolic y by sin x into sin hyperbolic y into sin x sin hyperbolic y by cos x into cos hyperbolic y is equal to minus 1. Therefore, the verification follows. Theorem: real and imaginary parts of analytic function satisfy Laplace's equation, or if fz is equal to u plus iv is an analytic function of z is equal to x plus iy, then uv satisfy Laplace's equation. Or if fz is equal to u plus iv is an analytic function of z is equal to x plus iy, then u and v both are harmonic functions. Proof: let fz is equal to u plus iv be an analytic function of z. Show that Cauchy-Riemann equations ux is equal to vy and uy is equal to minus of vx are satisfied. We have to show that Laplace equation del 2u is equal to 0 and del 2v is equal to 0. Differentiating equations 1 and 2 with respect to x and y respectively and adding them, we have del 2u by del x2 plus del 2 u by del y2 is equal to del 2v by del x del y minus del 2v by del y del x. This is equal to 0. Or del 2u by del x2 plus del 2u by del y2 is equal to 0, or del square u is equal to 0. Differentiating 1 and 2 with respect to y and x respectively and adding them, we have del 2u by del y del x minus del 2u by del x del y is equal to del 2v by del x2 minus of minus del 2v by del y2 is equal to del 2v by del x2 plus del 2v by del y2, or del 2v by del x2 plus del 2v by del y2 is equal to 0, or del square v is equal to 0. This proves the theorem.